Afternoon. Um, I've been talking, well, we have been talking about um, about what? Okay, theory and C star algebras, right? Okay, but when you say K theory, that means two things, even in connection with C star algebras. And I mean, there's a branch of K theory called algebraic K theory, which talks about rings instead. That subject ideals aren't even called rings. The rings are supposed to have a unit. But, in the setting of C star algebras seems to be quite important to be urbanic algebras. So it seems to be quite important to work without a unit. For instance, the idea of the suspension of urbanic algebra is quite important for working for understanding and proving understanding and working towards proving Watt periodicity. Chris, do you know what Watt periodicity says? You know who Watt is? Well, okay, but next week you will know, right? Good. That's I sometimes try to take on a rough countenance of a traditional professor. The late Abraham Kirchberg sometimes did that. He was very kind, but occasionally he liked to be gruff. For instance, have I told this story in the middle of a lecture at the Fields Institute program in 1994, 95, 96. Waterloo was closed in Waterloo, and we didn't know when it moved here. Fields Institute set up here. So he was talking about his work and other people's work on the classification of future algebras. It was quite hot then. He and I had both just finished talking at the International Congress of Mathematicians in Zurich, announcing results about classification of future algebras in K theory. Well, at one point, because of how the subject is constructed, Professor Kirchberg started talking about the property of quasi-diagonality. Algebra can be quasi-diagonal. A single operator on the Hilbert space can be quasi-diagonal. I guess the terminology was introduced by Paul Helmholtz. But, all right, so someone in the audience, fairly good-sized audience, students and postdocs, and some. He's also quite a number of faculty members. I was there. But, someone put up their hand and said, "What is quasi-diagonality?" Have I told this story? Yeah, I have. Oh, well, okay. How many people remember? Have heard it? Well, okay, but it's worth telling again. I think. Okay, so Professor Kirchberg stopped and he said, oh, "I'm just you can close the door. I'm just describing Professor Kirchberg's lecture where someone asked about quasi-diagonality, and the idea is that he wasn't in real life he wasn't rough, but he maybe sometimes like to pretend he was. I don't know. Maybe he was. Maybe he was. Anyway, his reply to the question, "What is quasi-diagonality?" Quasi-diagonality is a very important concept. Everyone should know what quasi-diagonality is. and then he just continued. Is everyone, I assume everyone here knows what quasi-diagonality. Okay, but it basically means that you can almost map the C-square algebra into finite dimensional C-square algebra. Okay, you can't map it exactly, but you can map it approximately. Okay, your linear maps which are approximately multiplicative, approximately more conditions on, but some of them follow from very robust concept, very important. Okay, so what periodicity you talk about the suspension. One way. Of course, there's the general six-term exact sequence, which is doesn't mention special C-square algebras. You just have a extension or Banach algebras, closed ideals of Banach algebras, and then homomorphisms. You assume that you're working with Banach algebras, you assume that the homomorphisms don't increase the norm. And the thing is, the reason I mentioned Banach algebras a lot is that to prove Gauss periodicity, following the proof in the textbook, there are other proofs. That would be a good exercise for someone, a good project for someone to look into some other proof of Gauss periodicity. But the proof in the textbook has to work with Banach algebras, okay? Not C-square algebras, because well, that mean it has to. Anyway, it can't work with unitary. Doesn't work with unitary elements. K1 defined in terms of unitary elements. Anyway, this is one way of doing it in a C-square algebra. It's easy to show that it's Banach algebra K1 for a C-square algebra can be constructed in terms of unitary connected components of the unitary group. But the trouble is, well, we'll see how we see why the proofs of Banach algebras, why in that case unitaries are irrelevant if you have to talk about invertible elements. And the K1 group for unital Banach algebra is look at invertible elements, modulo the connected components, and then follow the group, look at the connected components, and almost every divide by the group. And it's actually the component is open, so the quotient group is naturally the quotient follows the accountable group. That's the K1 group. For the C-square algebra, and whether you talk about unitaries or invertibles, it's the same because the polar decomposition, every invertible element is a product of the unitary element and the positive self-adjoint element. Unitary on the left, say positive element on the right, and that's the element of the algebra. Okay, but you approximate, suppose you have a unitary element, and you have an argument which involves approximating the unitary element by something. But a priori, you don't even know is invertible. Okay, that's how the proof goes. In a certain setting, if you want to talk about unitaries to begin with, then to proceed, you have to approximate by invertible elements. This invertible element has to have certain properties. But you could just say, well, if the unitary is invertible, so approximate it by itself. Well, that doesn't work because of the property you want the approximating element to have. And we'll see that, or you can peek in the book. And so the point is that the invertible element, if the element is close to the unitary, and because the unitary is invertible, the element that's close to it will be invertible, but certainly it won't be unitary. Okay, so I mean that would be completely expected. Even if you're in a C-star algebra. Okay, but so but it's quite easy to prove it in the Banach algebra K1 defined in terms of invertible elements. The C-star algebra gives you the same thing. And as we talk about unitary terms. Another way of defining K1 is in terms of suspension. You take the suspension of a given Banach algebra, and then you look at the K0. This is true over the reals too. It doesn't. It's not deep. You have to work with it. But we can talk about that sometime. It's a good thing to think about. If you look at the paths of projections, then how do those give you unitaries? Well, roughly speaking, if you have a projection and a path of projections connecting them, then it's the projections are close, then there's a partial isometry which goes from one to the other. Okay. It's even essentially unique. You can take the product and look at the because it's so close to being a projection, it will have a polar decomposition. It will be the product of the positive element and the partial isometry. That partial isometry is what I'm talking. If you have a given path, you break it up into a lot of short paths. You get a whole lot of partial isometries between the corresponding projections. And so you combine them, the partial isometries from here to here, and here to here. There are arrows, you can just combine them with the partial isometry going from here. It's isometric on the projection. The partial means, and zero on the resolving complement. And then the onto takes this projection onto that. You can think of what onto means in terms of action on the Hilbert space, that the subspace on which it's metric taken on range of the subspace. That's how you compose partial isometries. And if you do keep on doing it all the way along the path, then you get a single partial isometry going from the beginning to the end. Okay. And if suppose that the end projection is the same as the one you began on this path. Okay, so suppose that actually didn't stop here, went all the way around the beginning. Okay. Then you just go all the way around your partial isometry, finding all the ones over the short steps. Okay, well, this partial isometry will take this projection onto that one. That's called a partial unitary. And so if you cut down by that projection, it's unitary inside the cut down algebra. And that's considered to be a fair game for a K1. That's a K1 element. Okay, so that's so if you have if you look at the suspension, then it's paths in the algebra with unit adjoint. So So you the path of projection and maybe in a 2 by 2 matrix algebra. This projection maybe is 1, 0, 0, 0 in the algebra. And 2 of A. So I only piece of chalk. I brought that bring be long enough to hold. Oh, okay. I do have another. All right, so so we're looking at a path of projections going from here back to here, and it's and it's okay, so it's a closed path, and that's a element that gives you an element K1 of the suspension because it's a non-unital algebra. How do you define K1? You join a unit, okay? And it's K0 in a non-unital to define everyone know your work with that. You have a non-unital algebra. If you join a unit, then it's unital. And you can define K0 in terms of production. For modulus, remember with modulus, you can bring as a unit. Okay, then you somehow throw away the class of the unit. Meaning, if you take the plus the complex multiples of the unit, then you map it just to complex multiples of the units. Total A plus lambda 1 goes to lambda. You can see complex. Then A goes to 0. This is an algebra map, and because K0 is a functor for unital algebras, that's well known. You got K0 of this plus K0 of that. Well, and when it's complex numbers, K0 is non-zero. So the kernel won't be everything. It'll be a kernel. It'll be a kernel of K0. K0 plus K0. And of course, it's for definite. Kernel. And that's defined to be K0 array. One reason you have to do that is let's make the 6 term exact sequence work. Okay. Now, if it's K1 we're talking about, we do the same thing. You're joining unit and you've got K1 complex. But actually, that's 0. The complex. The real numbers, you have to be careful, but you have to do the same as for K0. Because K1 is the scalars, the real numbers, is non-zero. What's an example of an invertible element of the real numbers, the algebra real numbers, which is not connected, which is not in the connected component of the identity? Jack? Dr. Pavan? Sorry? Yeah, yes, yeah, sure. Okay, so you have if you want the K1 of the suspension, sorry, K0 is K0 suspension is K1 defined in terms of unitaries and invertible. And then what periodicity says if you take the double suspension, then that's the same as K0. And of course, that's the same as K1 suspension. All right. But, so So this says that if you have the path of if something in the suspension, in K0 of the suspension, then you get a unitary, okay? And the fact that that's a map, that is independently connected component of that unitary independent of how you construct it. That's an exercise, yeah? And added map. Okay, one terms of unitary or verticals. So we get to graph K0, it's eventually K1. Now, how do you go in the opposite direction? You have something in K1, how do you get a path of projections? How do you get a closed path of projection? Well, you can use matrices, you go to 2 by 2 matrices. And you notice that if you look at the two projections, 1, 0, 0, 0, and then 0, 0, 0, 1. There's a path connecting them, right? The actual path you just rotate. And it doesn't matter as long as the algebra has a unit, and then it could be any algebra, any equal to the even the real number of rotating. Okay. The point is that this rotation is defined with respect to the equivalence between the two projections. So it's defined with respect to the matrix unit, like 0, 1, partial isometry 0, 1, 0, 0, which takes the second projection and first. Well, it depends on how much order you go. This connects the two projections. But if you suppose instead of the rotation of this projection and this one, it's defined with respect to this partial isometry. Okay, it goes from one to the other. But suppose that inside K1 of the algebra, you have a unitary. Okay. So I keep telling people to sit close to the front, and then you can't see. That's terrible. I mean, with the screen in the way. Very good. Well, yeah, actually, that's not the camera, is it?
No.
No. Okay. There's another screen here. Okay. Well, all right. Okay. So what do we do? I mean, so the idea is very, 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 very rough idea is you rotate from here to here, and then you go rotate back again. But if you just go along the same path, then that'll undo itself, right? But suppose you go back by a different path. Suppose instead of rotating with respect to 0, 1, 0, 0, if U is a unitary in A, then take the rotation with respect to the unitary. Well, U is a 1 by 1 matrix, and so put it in the upper right-hand corner of a 2 by 2 matrix. And another way of going from the second projection to the first. So you can rotate with respect to that. So rotate, and then that will take this one back to that one along a different path. And that gives you and that path, if you check, then that combined path will give you back that unitary. Okay? If you apply this procedure to it. And of course we're getting a closed path of projections. Doing. So that's how you. I mean, if you're going to really roll up your sleeves and write the proof out, might take a little more than the 5 minutes I've been talking. Okay, but that's a good exercise. Okay, or you can look it up if you don't want to have fun. If you want it to be a chore, then you can look it up. Well, I don't know. So maybe some people think that's fun. That's fun. You have to find the right keyword. Okay. Look at the plot periodicity. You need the complex scalars, and I showed why last time. Plot periodicity the extension I goes way close to sin for u, and one way over I. And you apply it to k0, and you get some short sequence. It's exact in the middle. That's not hard to prove. And same with P1, get a short sequence. Well, very short. It's not a short exact sequence. It's exact in all 3 places, and you'd have zero. You do have zero for the alpha, for the K0 group, and the K1 group. You don't have zero at the end. So it's not exact here and here. If you put the zeros in if you want, but you only get exactness in the group. Okay. And then you have the reason the zero map is irrelevant is that what you really have is a map down to K, which is the first term of the left of the second, the left of it, and then the same here. This is in the complex scalars, and I said well, and then the real scalars, also get a real or complex map. But the mirror image is what. So this map is easy to construct with complex scalars, as I showed last time. But prove exactness here and here, I don't really know how to do it in the general case. Okay. So what you do is do it in a very, very special case, which gives you this, that the K0 is double suspension. It's the same as K0. Okay. You do that. And then you notice that the K0, that because of the other thing, the K0 of S is K1, K1 S is K0, taking the suspension just flips. So you can flip this second even index or the odd index map going down here, and then you can prove that it's the same as the other map that I mentioned. Except the way to prove it is just to prove that this map has to be unique. Any map has to be unique, if it's always there. Okay. I have a couple of papers on uniqueness of spanning algebra index map. The index map of spanning algebra case. Important comment with the group basis also published in the same place by Ralph Meyer. So that's how you do it in the general case. You forget about the special construction that I said, but you do look at in the very special case where the A is well. I'll work B instead. So you have so I want B to be the quotient, and the cone over B be the Argel, and the suspension term. Okay. This is a special case, and it's going to tell us about okay. Well, the point is that what's the cone? cone is, well, with suspension, by the way, remember that it's functions on the line into your Vannic algebra, which vanish at infinity. Okay. Well, if you just say bounded, if you just say functions that converge to something at infinity, plus infinity, then minus infinity converge to zero, and that's the cone. Okay. And so if you then take the limit at plus infinity, then that gives you map onto B. And if you take the kernel, then that's things that vanish both at plus infinity and minus suspension. And it's easy to see that the cone is contractible. The K groups are zero. So, the way you see that, the cone, here's a continuous function that converges at infinity. Then look at it on the interval instead of looking at it on the open interval instead of infinity. And then extend the interval like this. Okay? Then extend the functions, which to the left extend them to be zero. Okay, to the left extend them to be zero, and to the right extend the functions to be constant. Okay, and then this is the same algebra with the functions on the whole line, which are zero to the at zero and to the left of zero, and are constant at one. If you think of the closed half-line starting point, then actually, if you just go to the procedure I'm talking about, so you now have a one parameter family of maps from this algebra into itself. Okay, you just slide the graph to the right. Okay, and that's thinking of it as continuous functions on the whole line. And slide the graph, just translate on the whole line. Then that means that this graph will move like this. Big moving picture of it. And after 1 unit of time, it will be zero on the interval 0 to 1. You forget about what it is off the chart. And then this is a continuous path of homomorphism, taking every element of the algebra to zero. So the K in particular, K0 group, the K1 group, zero. If you look at this short exact sequence, you see those Vannic algebra. And take the six-term exact sequence of K groups. Well, we don't have 6 terms yet. When we're finished at 6 terms, at the moment, it's well, the terms are 6 terms, but we don't have the complex index number. We just have the what is it? K0, K0 is the suspension. K0. That's what K0 is. And K1 K0 K1 of the column and from and K1 B. And then we do have the index map coming up like this. But then that says that we have the map from K1 of B to K0 S of B is has zeros on either side, so it's isomorphic. And that's let me see. Okay. Well, in either case, no. What we have is the okay. What am I actually trying to do? I'm not trying to prove periodicity from scratch, which is with Yeah, right. With the index map that always exists, you do get that K1 of B is isomorphic to K0 of expansion. Okay, so that takes care of that. So you don't have to, if you can prove that exactness, you don't have to go through this kind of long-winded argument that I was talking about. Okay, that's not a way of doing it. There are two ways. Assuming that we can prove exactness, the two endpoints for the ordinary index map. And that's not such a big deal, okay? Well, this isn't such a big deal either, but maybe this is a little more elementary. That's more elementary, maybe this is more, okay, so as Pouyan says, you're Pouyan, it's dark, I can hardly see. Maybe it's because I'm getting the third degree, so, okay, but, so we would get the well, this is sort of blah. We don't need it because we have another approach. But the other one, well, it's interesting that this applies. But then the if you did have the other map, well, we have if we had the other map and exact, that would say that K0 would be isomorphic to K1 of S of B, which is the and then we could use that to flip the diagram in the general case. But conversely, if you what that shows is this diagram in the general case does imply block periodicity. So that's why this is equivalent to this. It's considered to be equivalent to block periodicity. It's called the sixth term fancy of block periodicity. Well, so I define this map. Then eventually, this turns out to be the map that you get from here to here. In the map that I constructed in a elementary way, without proving exactness, it turns out to have exactness here and here. At least because by uniqueness of just having a map. Okay, nothing else. But, so, but the standard approach then to proving block periodicity is hard. You have this map here, very simple map, but prove exactness in either place on either side of the map. In the general case, it's tricky. Well, I haven't actually seen how to do it. Okay, directly just by showing that you do get a map by flipping the index map. Block periodicity, and then proving uniqueness of its connecting map. Of course, for every map, if you multiply it by -1 into abelian groups, that's also has the same property. So you take care of that. The same. The uniqueness means globally unique for all cases up to a factor of plus or -1. In fact, if you're just saying it's a map, then place the map, it also works. Okay, so you have a map like this, find in all cases in a natural way, then it must be some multiple of the standard map. Okay, just some integer multiple in all cases, the same integer multiple in all cases. Therefore, you get when coming from block periodicity is either plus or minus this one silly one that I constructed. Okay, so there's an exercise to check whether it's plus or minus. Okay. But I guess it's not, but that's enough to check on just one case. You take a case, take this case. Okay. So you look at the case where you can actually physically construct map going from these are all there. Okay, one yesterday. You the degrees with the silly one with the instructed. That's not hard. There's a, if you like the silly map here, you even say that we take the silly map here, which is very easy to talk about. And you prove that you get 2 minutes points. Okay, well, of course, we'll come back to this. I think that's another discussion of this. I think. Of course, there'll be questions. There'll be all kinds of questions. There's a notice. There's well, every Friday there's the tutorial office hour. Tutorial. Not sure. 180. Sure. And there's almost enough room for. Not quite. Unfortunately, there are no windows for people to lean out. I'm referring to what the director of this program, the fields program that I mentioned 30 years ago. When I filled all the offices to overflowing, he said, well, I really like to accommodate your guests, even though there's a lot of trouble with visas and stuff, and they may have to, some of them may have to lean out the window. Okay, well, sometime, of course, I want to go back to Pascal's final. That's really very nice, down to earth. What's the conclusion, by the way? What's the basic conclusion? Funny, the conclusion is nothing to do with K-theory or C-state algebra. Just says it talks about measures, probability, positive measures on the 0, 1. Okay. Last time I covered in rough discussion just about everything except the I didn't talk about the proof of Klein's theorem for extension theorem for order vector spaces, order unit vector spaces. You have an element, order unit, element. But if you take positive multiples of eventually figure it out. Okay, but that gets used, and of course, just like the Banach theorem, uses the absolute choice. Then I also prove that there are 2 order structures on the ring of polynomials that happens to be rings, multiplication polynomials, right? And both of them, those happens both make it into an ordered ring on product of positive elements. Positive. If you take the Pascal triangle order, then it's easy to see what the positive functions are. Okay, that's just put positive. That's just putting compatible positive numbers in Pascal's triangle. To look at the positive functions on x, pointwise, the strict pointwise order on the interval 0, 1. Look at that ordered ring. Then well, you just look at it as an ordered group. What we want to do is compute the to be able to apply Klein's theorem to prove that if a polynomial is positive in the order we're talking about, strict pointwise, strict positivity on the opening. If we want to apply Klein's theorem, then we really have to know what the states are. We have to know what the states are. Okay, positive most by state I mean positive function, which is equal to 1 on the constant. So okay, so we and by the way, if something is if something is positive in the polynomial is positive in the sense that it's a finite sum of monomials in x and 1 minus x, then of course if the functional is positive on point, those things are strictly positive on the open interval, they're non-zero. And so a functional which is positive on such things would be positive on the monomials, right? If we want to go the other way around, we want to prove that if something is positive on the sums of monomials, then it's positive on pointwise positive things. We want to show not only that it's positive on things that are strictly positive in the interior, we want to show it's strictly positive on things that are strictly positive on the closed unit interval. Because Klein's theorem only talks about things that are strictly positive for every function. These ordered groups are lots of things that are zero for some function, and we can handle those. We can handle those because we just divide out by monomials till we get them to be strictly positive. And then we have to know that if something is strictly positive, if such a thing, for such a thing, we want to know that for the pointwise order, we want to know that every functional is strictly positive in such a thing. And so what's obvious is if you take the things that are strictly positive on the closed interval 0, 1, and of course every measure, if you take any measure on the interval 0, 1, then that will be strictly positive. Any non-zero measure, probability measure, and it will be strictly positive on anything which is strictly positive on the closed interval. But if it's okay, so what we have to do is prove that the states on the polynomials with the pointwise order, we have to prove that they're just evaluation at some measure on the closed interval. Okay, it sounds a lot like constructing a measure in the Hausdorff moment problem, doesn't it? That's essentially what we're doing. That's if you want to. The Hausdorff moment problem says there is a measure with certain moments, right? Well, that's what this does. That's where that measure comes in. If you analyze things, well, all right, we're close to the goal. Probably I shouldn't take advantage of the fact that there isn't literally a bell. So I like to interpret things thoroughly. But okay, but so we have to show that, in particular, that the extreme points, well, actually, what we actually have to prove is that if you have something strictly positive, then the functional is strictly positive. One is strictly positive on the closing. Well, it's enough to show it for the extreme points. Okay, enough to show it for the extreme points. If you know it for all extreme points, then you know it for the average of, because there's a measurement for average extreme points. Arbitrary point in the fund. complex set. So we want to know the extreme positive functionals are points valuations. That's what we want to know. But it just happens that extreme positive functionals on an ordered ring, order unit, extreme positive functionals are just which are equal to 1 on the order unit, phi of 1 equals 1. Those functionals are exactly the homomorphisms into the real line. It's just exactly like a C-star algebra, commutative C-star algebra. The pure states, extreme states are well, they're homomorphisms into the complex number. They're non-zero homomorphisms into the complex number. Here it's into the real numbers, so we just have real scalars. So this gets used. Here it gets used. I just reviewed quickly the structure theorem for commutative C-star algebras, and I don't think it talks about homomorphisms, of course, but then interpreting in terms of maximal ideals, maximal power ideals, not in terms of pure states. So at the moment, I think it's just an interesting fact related to the basic theorem. You can check that. Okay, but here it's important, so we should actually check that you have an order ring, an order unit ring. Then you have an extreme positive functional, which is normalized extreme state, and then it is preserves products. Okay, but then if it preserves products, it's by that x plus 1 minus x equals 1. So it's these are positive. These are positive. So its value on x and 1 minus x will be something positive, and so have some 1. So there will be some number between them. So that means on x it would be phi of x would be between 0 and 1. But then for an arbitrary such number, you get a homomorphism, just point evaluation on this closed interval. Okay? Because something is strictly positive in the interior, it's at least positive on the whole closed interval. All right, so that's the calculation of the that's the basic proof of the Hausdorff theorem. I don't want to let the cat out of the bag yet, but in an ordered ring, how do you prove that extreme state has to be non-applicable? You could try to look at the case of the commutative C-star algebra too, prove there that the extreme state has to be non-applicable. And of course, both of those things you can work out. Maybe the C-star algebra one is a little easier. Any questions? Well, lots of questions. Another thing I want to talk about is not to invoke. It's really so tempting, I can't resist the presentation. 50 projections, okay? 50 projections from the quotient if the ideal is AF. In general, there's a big exercise in the book to show you can't do it in general. You definitely can't do it, but if the ideal is AF, it's not even enough for the ideal to have K1 equals 0, okay? So because there are other properties of AF algebras that come into the proof. But using those other properties, there's some slightly technical limits, okay? A couple of slightly technical limits, which not about lifting projections, just about AF algebra. Well, it's a special case if you have an AF algebra and you have a projection gets a join to it, not the unit, but if some projection that gets a join to it, then the resulting algebra, that's a special case of AF by AF, because the quotient is just a complex number. And that we have to prove that particular algebra is AF. that follows. That's after you've already lifted the projection. So there's some technical limits which I'm just giving. Maybe I'm just going to assume them always, but permanently. I have some thoughts. I have something. It's exactly for this purpose.
Okay.
I knew I was going to spill something. So what I wanted to do is just purely fun with no technical, applying some technical lemons, but not proving it. So it's very easy to lift projections. Because the sixth term exact sequence says if this is zero, then that means that you have certain activities, you can lift K0 elements. So therefore, you should be able to lift projections, right? And you actually can, but it's an argument which has some surprises. So it's an entertaining. Too bad there's no exam because it'd be something nice to put on the exam. Once we do it. Okay.